Hi everyone. We're going to have our next lesson on radicals, and what I'd like you to do is simplify these. This is read the cubed root of 8. This is read the cubed root of negative 8. This is the fourth root of 81. And this is the fourth root of negative 3 to the fourth. This is the fifth root of negative 32, and this is the sixth root of negative 1. Okay, try these problems, pause the video, copy these down, and we'll continue. Okay, so let's go over these problems. So the cubed root of 8 is 2, and the reason is because 2 to the third is 8. The cubed root of negative 8 is negative 2, since negative 2 to the third is negative 8. The fourth root of 81 is 3, since 3 to the fourth is 81. And the fourth root of negative 3 to the fourth, which is really just 81 again, is 3, since negative 3 to the fourth is equal to 81. But notice that's positive 3 to the fourth equals 81. The fifth root of negative 32 is negative 2, since negative 2 to the fifth is equal to negative 32. And the sixth root of negative 1 does not exist. We say this is imaginary. We cannot take a number to the sixth power and get an answer of negative 1. So on our second day with radicals, we noticed some very interesting properties. We can write a radical this way, where B is called the radicand, N is called the index, and this is the radical symbol. And if we set x equal to the nth root of b, by the do now, we see that this means that x to the n equals b. Okay, now a few interesting properties. The nth root of b to the n is equal to b when something is true of the index, and the nth root of b to the n is equal to the absolute value of b when something is true about the index. So let's take a look at the do now to give us a hint. If we take a look at 1 and 2, we see that the cubed root of 8 is 2 and the cubed root of negative 8 is negative 2. So we could safely say that if we write negative 8 as negative 2 cubed, we could safely say that the nth root of b to the n is b if n is odd. But if n is even, just like in number 4, we notice that the fourth root of negative 3 to the fourth is just 3. Just like the square root of negative 9 squared is just 9. It's always understood to be the positive root when the index is even. So absolute value is needed when the index is even. And then, of course, a few properties of radicals that are true with square roots. When we want to simplify, that is. and that is that the nth root of the product of two numbers is the nth root of the first times the nth root of the second, and the nth root of the quotient of two numbers, provided that the denominator is not equal to 0, is the nth root of the numerator divided by the nth root of the denominator. Okay, so let's see how we could use these properties. Let's simplify the following. The cubed root of 25 times the cubed root of 10. Well, this can be written as the cubed root of 250 using the product rule. And we could do one of two things. We could prime factorize 250, or we could recognize that the first perfect cube factor that goes into 250 is 125. We could rewrite this as the cube root of 125 times the cubed root of 2, which becomes 5 times the cubed root of 2. Or if we take the cube root of 250 and prime factorize it, let's see what we get. We get the cubed root of 5 cubed times 2. So we have the cubed root of 5 cubed times the cubed root of 2, and that's just 5 times the cubed root of 2. So these are two ways where we could simplify a cubed root. I think prime factorization is the way to go. All right, let's move on to the next page. All right, now let's do one by ourselves. Let's do, this is problem, I believe, number 8. I believe it's 8. I'm taking a guess, but 8. Let's simplify the cubed root of 54 minus the cubed root of 16. Okay, try that by yourselves. Pause and then restart the video. All right. Well, we could factor 54 into 3 cubed. Let me just erase that because that doesn't look right. Okay. 3 cubed, which is 27 times 2. And 16 is just 2 to the 4th, which we could write as 2 cubed times 2. So if we separate these, we get 3 times the cubed root of 2 minus 2 times the cubed root of 2. And because the radicals match in radicand and index, we could almost treat these as an x and combine like terms. So 3x minus 2x is 1x, or we could just say 1 times the cubed root of 2, or just cubed root of 2, which is just as good. Okay. Now let's take a look at expressions that have variables. So I'm going to write a few. Okay, so number 9, wrong color again. Number 9 is the cubed root of x to the 4th, y to the 5th. Number 10, simplify that. The cubed root of 24 times x to the 7th, y to the 11th. And let's try another one. How about another index, like the 4th root of 80, y to the 14th. And number 12, the 5th root of 32, x to the 10th, y to the 6th, z to the 7th. And then let's take a look at these Number 13, the cubed root of m cubed divided by m to the 7th. And 14, the fourth root of 486 m to the 11th divided by the fourth root of 3m to the 5th. All right, copy these down, think about them, and we'll discuss it. And pause the video, and we'll get back to them. Okay, let's start on number 9. All right, now if we prime factorize, this is prime factorized, but we could split this up into multiples of 3. The first one is x cubed times x, and the second one is y cubed times y squared. So if we take these and find their cubed roots, the others remain. And since multiplication is commutative, we could write the cube root of x cubed y cubed times the cubed root of xy squared. So the answer is just xy times the cubed root of xy squared. And this would be considered simplest radical form. Okay, so let's take a look at the next one. The next one can be written as the cubed root of, well, 24 is 8, which is 2 cubed times 3. And again, we take out x to the 6th times y. The highest power of y there is to the 9th times x times y squared. Now notice that we picked multiples of 3, the highest multiple of 3 that we could find in the exponent. And if we group those together, oops, sorry, lost my pen there. Let me erase this. Oops, wrong thing. Let me erase this. Technical difficulties here. Oh, I can't erase that. I don't know what happened, but I'll use my pen again. Okay, so I could rewrite this as the cubed root of 2 cubed times x to the 6th times y to the 9th. And I'm going to erase this other part of the radical. Oops, wrong eraser. I'm going to erase this part of the radicand. Let's see if I could erase all this. Okay, and get y to the 9th. Oh my gosh, I have to get used to this. Y to the 9th. All right, so I took all those out, times the cubed root of 3xy squared. So the cubed root of 2 cubed is 2. What's the cubed root of x to the 6th? That is x squared. X squared times x squared times x squared is x to the 6th. And what's the cubed root of y to the 9th? That's y cubed. Since y cubed times y cubed times y cubed is equal to y to the 9th times the cubed root of 3xy squared. And that would be the simplest form for that particular problem. Okay, now hopefully we see a pattern here. The easiest way to do this is to divide the index into the exponent. So 3 into 7 is 2 with a remainder of 1. So we know that that's x squared, and then x remains in the radical here. And 3 goes into 11 3 times with a remainder of 2. So we could easily get the cubed root simply by dividing the exponent into the index into the exponent. As far as the coefficient is concerned, we would have to prime factorize it. So for the next one, the fourth root of 80, well, we would have to prime factorize that, and that's the fourth root of 2 to the 4th times 5. That's 16 times 5. And y to the 14th, well, again, that's y to the 12th times y squared. But using our little shortcut, we have the 4th root of 2 to the 4th times y to the 12th. And we're left with the 4th root of 5 times y squared. And this becomes 2y cubed times the 4th root of 5y squared. Note that technically, because the index is even, an absolute value should belong here, but I will not mark it incorrectly if you don't put the absolute value. I'm just doing that for emphasis. Okay, now let's try the 5th root of 32, x to the 10th, y to the 6th, z to the 7th. All right, so again, 32 can be written as, I believe, 2 to the 5th. And then x to the 10th is really 6 to the 5th squared. And y to the 6th is y to the 5th times a y. And z to the 7th is a z to the 5th times a y squared. And I'm going to extend this radical sign here. So because these are perfect fifth roots, our answer is 2 times x squared. And you could have gotten that by using the shortcut. 5 into 10 is 2. And y, z, times, this should have been a z squared. So wait, let me just correct that for a minute. This should be z squared. I wrote a y by mistake. That should have been a z. So let's put the pen back on. This is z squared. So that would be 2x squared yz times the square root of yz squared. Okay, and again, we could have used that shortcut, 5 into 7. The 5 into 7 is once with a remainder of 2. So we put the 2 in there. And 5 into 6 is once with a remainder of 1. So that would be our answer in simplest form. Okay, in the next problem there, we could use that property that we can divide within the radicand. And the rules in dividing with the same base is we subtract the exponents. And we could use that shortcut that the cubed root of m to the 6th is simply m squared. And we're done. Similarly, for this one, we could write the 4th root of 486 m to the 11th divided by 3m to the 5th. We divide the coefficients and we get there 162 m to the 6th. But 162 can be written as 3 to the 4th times 2. And m to the 6th is m to the 4th times m squared. So our answer there is the 4th root of, the 4th root of, I lost my pen again. The 4th root of 3 to the 4th m to the 4th times the 4th root of 2m squared. And the answer there is 3m times the 4th root of 2m squared. And again, because 4 is even, there should be an absolute value there. I should say because the index 4 is even, there should be an absolute value there. All right. Now, our next role is to simplify a fraction like the following. The cubed root of 27 over 5. All right, now if we separate it, like we did the others, we have the cubed root of 27 divided by the cubed root of 5. Now the cubed root of 27, I believe, is 3. But this fraction is not simplified because there's a radical in the denominator. So we have to rationalize the denominator. And with square roots, we just multiplied by the denominator over the denominator because we get the denominator squared. With cubed roots, we want to get the denominator cubed. So this is what we do. We multiply the denominator by the cubed root of 5 times the cubed root of 5. And we have to multiply the numerator the same way. So when we multiply, we get 3 times the cubed root of 25 divided by the cubed root of 5 cubed. Well, that's equal to 3 times the cubed root of 25 over 5. And now we have rationalized the denominator. So that's what we do when we want to rationalize the denominator with cubed roots. With fourth roots, we do the same thing. We would multiply the denominator with 3 factors, so we have the denominator to the 4th, etc., etc. All right, let's go to the next page and take a look at a binomial denominator. Let me just peek. I'm up to number 16. Sorry about that. 16. Okay, let's do number 16 over here. Now, if the denominator is a binomial radical, maybe I meant to do, sorry. Actually, I'm going to erase this. I'm going to change the problem. Let me do, change the problem a little bit. Okay, I think this one's easier to begin with. Let's do 2 over 1 plus the cubed root of 4. Okay, now this denominator is a binomial. Now, recall that when we had just 2 over 1 plus the square root of 4, we multiplied the top and bottom by the conjugate, which was 1 minus the square root of 4 over 1 minus the square root of 4. And that gave us 2 times 1 minus the square root of 4. And this was the difference of 2 squares, which was a squared minus b squared, or 1 minus root 4 squared, which was 2 times 1 minus root 4 divided by 1 minus 4. And that gave us an answer of 2 times 1 minus the square root of 4 over negative 3. So notice that here we used an important property that a minus b times a plus b is equal to a squared minus b squared. And when we square a square root, the radical sign disappears. Well, in this problem here, we want to make the cube root disappear. So we go back to these 2 formulas. A cubed plus b cubed, the sum of 2 cubes is equal to a plus b times a squared minus ab plus b squared. Notice it's SOAP. It's the same, opposite, and always positive. Okay? So in this problem here that I gave you, the 1 plus cubed root of 4 is the a plus b part. So we want to multiply that by this trinomial here so that I could get the sum of 2 cubes. So if a is 1 and b is the cubed root of 4, then a squared minus ab plus b squared becomes 1 squared minus 1 times the cubed root of 4 plus the cubed root of 4 squared. Now, I didn't get to this, but the cubed root of 4 squared is also equal to the cubed root of 4 squared within it. So we could rewrite this as the cubed root of 16. So let's go back to our problem. So this is just a side note. This is also a side note. Okay, and now we're going to go back to a problem. So I'm going to rewrite my problem here. And what we're going to do is we're going to multiply the top and bottom by 1 minus the cubed root of 4 plus the cubed root of 16. And that is this expression over here that I'm underlining. Over itself, don't forget to multiply over itself because it is a form of 1 and we are not changing the value of the expression at all. Okay, so what do we get? We get 2 times this expression divided by, now we could use the sum of 2 cubes. This product here is equal to a cubed plus b cubed. Well, if a is 1 and b is the cubed root of 4, we have 1 cubed plus the cubed root of 4 cubed, which gives us 1 plus 4, or simply 5. So this is all over 5. And that is rationalizing a cubic binomial denominator. Okay, and this is considered simplest form, believe it or not. We can't do anything else with it. So I'd like you to try 2 by yourselves to make sure you understand it. Okay, try these. I'll write them down. You'll pause the video and see what you could come up with. Okay, 17. Okay, I'll give you one like the first one. Okay, so the one I'd like to give you is the cubed root of 64 over 7. And the second one I'd like to give you is, okay, I have it here in my notes. Let me just get it out really quickly. Okay. 3 over Okay, I think that I didn't really pause it. You might have seen me writing a few things. I'm not sure, but 17 is completed. We multiply the top and bottom by the cubed root of 49, actually. And in 18, we use the difference of two cubes. A is 2, B is the cube root of 5, as I indicated here. Substituting it into the formula, the A cubed minus B cubed comes out to be 8 minus 5, which is 3. So when we multiply the top and bottom by this expression, we get 3 times that trinomial over 3, since these multiply to A cubed minus B cubed. And our answer is just 4 minus 2 times the cubed root of 5 plus the cubed root of 25. Okay, I have a few more I'd like to show you, and I'd like to give you one for extra credit. Let's go to the next page and see. Page number am I up to? Oh, 19 I'm up to. Okay. Oh, all right. Oh, I'm up to, wait, let's look at 19. All right, so for 19, how would we do this one? 6 over 4 minus 2 times the cubed root of 5 plus the cubed root of 5 squared. How would we simplify that? Let's see. Let's try. Okay, that's it. That's the only one I wanted to do. And for extra credit, and I found these in my notes, if I could just find them here, because they're all over the place. The ones I wanted to do as a challenge are these. What would happen? Oh, wait, where did I put those? Wait, I just have to pause a little bit because I wanted to get the challenge problems here for you. Oh, here it is. How would we simplify these? 2 over 2 minus the 4th root of 2, that's 1, and 2, 10 over the square root of 2 plus the cubed root of 3. We have never talked about mixed indices, so think about those. But going back to number 19, I could find that again. All right, so we look at the denominator, and it looks like it would be the sum of two cubes, if we recall the formula. A cubed plus B cubed has the one where it's A plus B, the same, and the opposite in subtraction. So this trinomial matches this, which means that A squared must be 4, so A is probably 2. Well, AB is 2 times the cubed root of 5, so we know what B is. B is cubed root of 5. And the B squared is the cubed root of 25, which is the same as the cubed root of 5 squared. So in order to simplify this trinomial cubic denominator, I shouldn't say cubic, cubed root denominator, we would multiply the top and bottom by this factor, A plus B. And A plus B is simply 2 plus the cubed root of 5 over 2 plus the cubed root of 5. And when we multiply those, we get 6 times, oh, wrong color again, 6 times 2 plus the cubed root of 5 over, and now the product of these two would be our A cubed plus B cubed. So the A cubed plus B cubed here, and I'll write it down here, is just 2 cubed plus the cubed root of 5 cubed. So that's 8 plus 5, which is 13. So we put that over here. And that's our simplification. We cannot divide through, and we've simplified it. Okay, so I may give you problems like this in homework, but try these if you have time and nothing else to do. You could try these for extra credit. All right, I hope this helps, and stay healthy, everyone. Keep safe, and I will speak to you soon. Bye.